Hello, everyone, and welcome to today's webinar. My name is Rula Deeb. I'm a senior principal at Geosyntec in Oakland and the coordinator of the series on behalf of SERDP and ESTCP. Today's event will consist of a brief overview of both programs, followed by technical presentations featuring DoD-funded research efforts to address challenges associated with PFAS analysis in environmental media. We'll start off with Janice Willey from the U.S. Navy, who will provide an overview of PFAS analysis, as well as significant challenges and ongoing efforts to address these challenges. Second, Dr. Jin Liu from McGill University will discuss progress towards improving PFAS analytical methods, particularly for PFAS originating from aqueous film-forming films, or AFFF. And then our third and final presenter will be Dr. Jennifer Field from Oregon State University. And Jennifer will talk about research efforts to determine the factors that impact PFAS stratification in water columns that may result in artifacts in measured PFAS concentrations. Each of the three presentations will be followed by a brief Q&A session, and we will conclude the webinar with another Q&A session featuring all of today's speakers. The next several slides provide instructions on optimizing your webinar experience. If you have not done so already, please download Zoom at the link shown here and provide it to you in your webinar registration confirmation email. If you cannot download Zoom, you may view the slides using a compatible internet browser such as Firefox, IE, or Edge, and by creating a free Zoom account. If you are unable to view the slides, or if your screen freezes, try keying Control and F5 to perform a hard refresh of your screen. If you are accessing the audio through your computer, click the arrow next to the Join Audio button, select Test Speaker and Microphone, and follow the prompts as they appear on your screen. And if you continue to experience difficulties, please call into the conference line shown here. You may also submit a comment using the chat box. Please use the chat box only for comments related to technical difficulties. We would like you to use the Q&A option for questions for the speakers and not for comments related to technical difficulties. You can also download a PDF of the slides from the webinar webpage and call into the conference line and follow the slides. We will also be live streaming the webinar on the SERDP and ESTCP YouTube channel at the link shown here. Just a reminder that today's broadcast will be listen only. You may submit questions by using the Q&A box on your screen. You do not need to wait until the Q&A periods to submit your questions. In fact, we do encourage you to submit them well in advance of the Q&A questions. And we ask that when you do submit your question, to make sure that you add your organization name at the end so that we can identify you. With that, I would like to introduce Dr. Andrea Leeson, who is the Deputy Director of SERDP and ESTCP, as well as the Program Manager for the Environmental Restoration Program area. Dr. Leeson has been with SERDP and ESTCP since 2001, and prior to that, she was a research leader at Battelle, where she conducted research on in-situ bioremediation and the design and implementation of innovative biological, chemical, and physical treatment technologies for site remediation and industrial wastewater. Andrea received her doctoral degree in environmental engineering from the Johns Hopkins University. Andrea, please proceed.
Great, thank you, Rula, and thank you to everyone for joining us today. Before we get into the presentations, which I'm sure you're very eager to hear, I'd like to give you just a little bit of an overview about SERDP and ESTCP and who we are and why we are doing these webinars. So first, we have two companion programs, SERDP, the Strategic Environmental Research and Development Program, and ESTCP, the Environmental Security Technology Certification Program, both of which are DoD's environmental technology programs. SERDP is the traditional R&D program that we operate in partnership with also the Environmental Protection Agency, as well as the Department of Energy. And what we're really looking to do here is take our research and direct it so that it impacts our real world environmental management. ESTCP is our demonstration and validation program, and what we do here is we take the innovative technologies or the knowledge that's coming out of SERDP or other research programs, and we're looking to bridge that so-called valley of death so that we can develop field measurements, field demonstrations of the technologies so that they are more ready for commercialization and use at the end user stage. So what drives us are two main drivers in terms of the sort of research we fund. First is this sustainment of our testing and training ranges, as well as facilities and operations on our military installations. And this is very broad, as you can imagine, and shown here are just a few of the issues that we address on these installations, everything from maritime sustainability to noise issues, climate issues, as well as dealing with munitions constituents. Second, we have this driver of reducing current and future liability. A piece of this is the traditional pollution prevention program, where we're looking to eliminate or minimize hazardous pollutants, materials, processes on our military installations. And then also we're dealing with contamination from past practices. This could be impacted groundwater, soil, sediments. And falling within this category is dealing with any emerging chemicals of concern that occur throughout the years. Now, certainly what we'll be addressing today is the whole PFAS issue. And I did want to give you a little bit of information about what we're doing on PFAS. And you'll see in the chat room, there is a link that will take you to this graphic here on our website. And I'd like to point it out because it is interactive, and from here, you can really see everything that we're doing on the whole PFAS issue. The graphic that you'll come to is interactive, and each of these boxes are live that will take you to a brief description about the topic, and will link you to web pages of the specific projects that were funded. So there's a tremendous amount of information available here. And the two presentations you'll hear today, three presentations, are all fall within this grand scheme of research on PFAS. Another very important piece to us in addressing all of these research challenges is to deal with the whole issue of the technology transfer of the information that we develop. This can take the form of videos, various types of guidance documents, manuals, in-person training, and then really a key part are these webinars. All of this information is available on our website, and the webinars have been very helpful to get the information out about the various SERDP and ESTCP projects. We have webinars coming out roughly about twice a month. Listed here are some of the upcoming webinars. Registration is live for all of these, and all of past webinars are archived, and you can find them at this at the webinar site that will be coming up on the next slide. I also wanted to point out that we have our symposium coming up this year. This is also a great opportunity to get a little bit of information about all of the projects that we're funding. That will be November 30th through December 3rd. The call for poster abstracts is already up, and so I do encourage you, if you would like to submit a poster or attend the symposium, please do check that out. Here is the link you can go to get information about the webinar series, to both register for upcoming ones as well as to see the archived versions. So please do visit that to get more information about those webinars. And at this point, I'll turn it back to you, Rula.
Thank you so much, Andrea. It is now my pleasure to introduce our first speaker, Ms. Janice Willey, who is a senior chemist for Naval Sea System Command's Laboratory Quality and Accreditation Office in Charleston, South Carolina. Janice's current area of focus is PFAS sampling and analysis. She has served as a member of the SERDP and ESTCP PFAS working group, providing technical review of DoD-funded projects. She is also the quality assurance manager of the SERDP-funded project responsible for validating an isotope dilution LC-MS method for PFAS in a variety of environmental media. Janice earned a bachelor's degree in biochemistry from Clemson University in Clemson, South Carolina. Janice, please get us started with today's first technical presentation.
Great. Thank you, Rula. Today I'm going to provide a brief overview of the analytical challenges associated with PFAS, DoD's current strategies for dealing with these challenges, and the DoD SERDP method initiatives that are an integral part of this strategy. The way I see it, there are four big issues that currently make PFAS analysis challenging for the DoD. First is a lack of published methods. What I mean by published methods are methods that have undergone a documented validation process that evaluates the method for a defined scope of media and target analytes. For the DoD, these methods have to be written in a manner that ensures minimal inter-laboratory variability when it's implemented by DoD ELAP accredited laboratories, and also facilitates acceptance by regulators. This typically equates to EPA published methods. Next, our target keeps changing. We have an ever-changing scope required for the methods. Years ago, we were primarily focused on drinking water and groundwater, but now for the DoD, the scope of media required can include surface water, leachate, soil, sediment, air, and biota, to name a few. On top of that, the list of PFAS we are being asked to evaluate is ever growing, and their associated reporting limits continue to be pushed lower and lower. And lastly, as the DoD is tasked with stepping away from fluorosurfactant-based AFFF products, we are challenged with creating methods to evaluate the replacements. Unfortunately, the chemistry of these AFFF replacements are yet to be determined. This creates a huge problem when you're developing methods in that appropriate sample preparation and analytical steps are dependent on the chemistry of the samples themselves. The EPA methods that DoD currently has at their disposal are EPA 537.1 and 533, and SW 846 method 8327. Currently, the DoD utilizes EPA 537.1 to assess drinking water in accordance with DoD policy. If the sampling and analysis scheme proposed for monitoring under UCMR 5 is adopted, this policy may change to include analysis using EPA 533 for some PFAS. The hazardous waste method 8327 that is currently published as a draft method is viewed by the DoD as a screening method only due to the limitations associated with its preparation procedures and quantitation scheme it utilizes. Therefore, it cannot be used for the collection of definitive data for DoD projects. So for all other media besides drinking water, we have no appropriate published method right now. In its place, the DoD's Environmental Data Quality Work Group, the EDQW, has published PFAS-specific analytical quality control requirements in the DoD-DOE Consolidated Quality Systems Manual for Environmental Laboratories, the DoD QSM. Laboratories performing analysis of all media other than drinking water for PFAS must meet the general requirements in the QSM, as well as the PFAS-specific requirements contained in Appendix B, Table B15, and Appendix C, Table C44 and C45. Table B15 is not a method, it is only a list of quality control requirements that are designed to reduce variability from laboratory to laboratory and to provide data of documented precision and accuracy. It is only a stopgap approach until an appropriate method is published. That brings me to our DoD SERDP method initiative. By far the largest and most complex method initiative the DoD and probably the EPA has ever undertaken is the 1600 series PFAS method initiative. This SERDP-funded and led effort is validating an LC-MS method that utilizes isotope dilution quantitation for the determination of 40 PFAS in groundwater, surface water, wastewater, landfill leachate, soil, sediment, biosolid, and tissue, a whole lot of media. It also includes a holding time study that covers a range of these media as well. SERDP is also funding a Naval Research Laboratory-led initiative that is focused on developing a method to determine total PFAS content expressed as total organic fluorine in those yet to be determined AFFF replacement products I spoke of earlier. The driver of this initiative is the 2020 National Defense Authorization Act, as it prohibits the procurement of AFFF containing greater than 1 ppb of PFAS after October 1st of 2023. While both of these initiatives are helping to address the DoD's immediate PFAS analytical needs, we know additional methods will most likely be needed in the future. SERDP-funded research projects and research methods they employ help to inform future method development efforts. Today, we are lucky to have Drs. Jin Liu and Jennifer Field speak with us about two such projects they are currently leading. Jin's project on developing analytical methods for comprehensive profiling of PFAS in AFFF impacted environmental matrices will most likely aid in the development of analytical methods for additional classes of PFAS, while Dr. Field's project on assessing and mitigating PFAS sampling bias will help the DoD improve their PFAS sampling protocols. They both have a lot to talk with you about, so I don't want to take any more of your time today. I just wanted to end with providing you a link to the EDQW's DENX webpage, where you can find information on EDQW products such as the DoD, DOE, QSM, and the DoD's PFAS data validation guidelines. And I thank you for your time.
Thank you so much, Janice, for a great overview. As a reminder for everyone in the audience, you can submit questions by using the Q&A box on your screen. We have received several questions on Janice's presentation. Janice, can you provide a timeline for when you expect the 1600 series method to be published?
That is the million-dollar question I think everybody really wants to know. Right now, the interlaboratory validation study is complete, and SERDP is working towards submitting the study report to the EPA very shortly. At that time, the EPA will evaluate whether they can post the method as a draft as a 1600 series method. While the EPA is doing their evaluation of the method, SERDP will continue on with the multi-lab validation.
Great, thank you, Janice. And from a quantitative perspective, how low can you get with the 1600 series method?
Okay, so we have a whole bunch of different media that this method covers. So of course it depends on the media type, but I'll give you an example. I'll use PFOA since everybody, we're mainly concerned or looking towards PFOA and PFAS these days to make decisions. For all aqueous samples, except for landfill leachates, it looks like about 1.6 ppt is achievable in these aqueous media. For leachate, it's about 8 ppt, and that's due to the difference in the sample volume that's utilized in sample preparation. For solid samples, except for biosolids and tissues, the limit of quantitation is about 0.2 ppb. For biosolids, it's double that, around 0.4, and for tissues, it's about 0.5 ppb.
Great, thank you so much. When the 1600 series method gets published, will table B15 from the QSM still be applicable?
Well, when the method's finally published, the EDQW is going to evaluate the requirements currently in the table and make adjustments accordingly. Those table Bs found in Appendix B of the QSM were created to promote consistency. They provide, by providing this set of minimal quality control requirements. But it's mainly for instances where you have multiple versions of a method, or the methods maybe say should instead of must on some things that the DoD felt really should be must, or maybe it wasn't clear and didn't provide enough detail or information on how to achieve something. Some of that information is often found in our tables, or we, frankly felt for some of our projects we needed more stringent requirements than the method. And in those cases, we make those clarifications in those B tables. So we have B tables for a lot of other methods. So I suspect that, you know, due to differences in programs, that we will have some clarifications that will be needed in the future. So I don't expect the table B15 to go away in its entirety, but I do expect it to be modified.
Thank you, Janice. This is a question from EPA Region 5. Are EPA and DoD working on resolving the issue with method A327 and DoD's position that it's a screening level method only? And do you expect DoD's position to change as these new methods get developed?
Well, currently we're developing a method for the media that are covered by 8327. That'll be falling under the 1600 series method. So all of the media that are addressed in 8327 are addressed as well as additional media by the 1600 series method. So we are looking to have that method published and finalized in the future, and look towards that method as a solution for the media such as groundwater, surface water, and wastewaters and such.
Great. And this is a question from the Metropolitan Water District. Does the 1600 series method include all the suggested PFAS listed in the draft UCMR 5?
Yes, that was a great question, actually. Let me clarify. The list of 40 analytes includes all of the analytes that are included in methods 537.1, 533, and 8327, as well as some additional analytes. So yes, it does.
Great, thank you, Janice. And one last question before we let you go. A lot of questions are coming in from various labs, and the question is related to how they can get involved, if that's an option, with the 1600 series method multi-lab validation. Is that an option?
So unfortunately, that process has already gone through. We solicited laboratory participation. Our contractor solicited laboratory participation for the multi-lab study previously. And I think that occurred, I believe, about a year and a half ago, actually. So unfortunately, at this point, that validation effort is moving forward with the laboratories that were previously selected. And I should note that includes 8 DoD lab accredited laboratories and 2 state laboratories.
Great. Thank you so much, Janice. We'll try to get to the remaining questions in the final Q&A session, depending on how we do on time. For now, I'd like to thank you again, Janice, and take the opportunity to introduce our second speaker, Dr. Jin Liu. Jin is an associate professor of civil engineering, a Shuang Situ faculty scholar, and the director of the Brace Center at McGill University in Montreal, Canada. Jin's current areas of research focus on developing analytical methods for emerging contaminants, including PFAS, the environmental fate of organic contaminants in both natural and engineered systems, and the development of remediation technologies for PFAS. Jin earned a bachelor's degree and a master's degree in environmental engineering from Tianjin University in China, and a doctoral degree with Dr. Linda Lee in agronomy with a focus on environmental chemistry at Purdue University. So Jin, please go ahead.
All right, thanks for having me. So today I'm gonna share some progress we made under the federal-funded project to improve chemical analysis for HOPF impacted samples. And a major focus is actually on the analytes that has not been included in the published methods. So I'll mainly talk about methods for water matrices and solid matrices such as soil and organic waste, and a biota samples such as fish and avian plasma, and present a few case studies. So my case study might not be always focused on samples or sites from the US, but I hope my international perspective can broaden our understanding of this large chemical class. Janice has provided excellent review of the PFAS Analytical Challenges. I want to emphasize that there's urgent need for PFAS biota methods, for risk assessment purposes, and also published methods. And most of the literature mainly focus on legacy compounds such as PFOS, PFOA. Their analogs of different chain lengths and also fluorotelomere sulfonates and some sulfonamides. But now, as we know, zwitterionic PFAS and also to a less extent, cationic PFAS make up a large percentage of PFAS in AFFF and has been detected at high level at impacted samples. So as some of these chemical standards are now commercially available, we need to figure out ways to include them in our routine analysis. So here are some representative structures. So the first one appears as a cation, so you can see positive charge on this quaternary ammonia group. And the other now appear as, zwitter ions with positive charge here and negative charge here. So zwitter ions have, strong pH dependent behavior, so they may become completely cationic or anionic in acidic or basic environments. Zwitterionic surfactants have always have many industrial applications, also use consumer products, so AFFF are not exceptions. And also throughout the project, although the focus is on AFFF, later I will discuss sources we discover can also contribute to these new molecules. Our first objective is to standardize methods for compound-specific PFAS analysis using LC-MS. So we hope to establish rigorous procedures for more than 50 analytes. And the sample preparation methods and cleanup procedures developed in task 1 will also going to be used in task 2 and 3, where we are improving and validating the top assay and the total organofluorine methods. Throughout the project, we've been just asking ourselves is how and can the knowledge and practice developed for legacy compounds be applied to the PFAS of diverse chemistry, and what kind of modifications are necessary. Here I show various type of matrices we plan to cover throughout the project. And at each project, we always start with water matrices and move on to soil sediment and then biota samples. So given the limit time today, I'm gonna only talk about the compound-specific PFAS analysis using LC-MS. I also want to mention, even though our project's meant for target analysis using triple quadruple mass spectrometry, we are also using high resolution instrument for quantitative, semi-quant, and a qualitative analysis at the same time. So this approach is gaining popularity, at least for academic labs. So if you have dealt with various water matrices, you probably know one of the challenges is their wide concentration range, from low parts per trillion to dozens, parts per billion, per millions. So after analyzing, thousands of samples, we now propose this concentration-based workflow. So if the concentration is over 5,000 nanogram per liter, for instance, for AFFF impacted groundwater from the source zone areas, direct aliquoting and dilution with a proper solvent is the way to go. So when the concentration is lower, definitely we suggest sample concentration using solid phase extraction, SPE. And such as for municipal drinking waters and for surface water far away from PFAS sources. And we also found that SPE method that developed for PFOS, PFOA actually are applicable for to zwitterionic PFAS. That means the same cartridges or same processing steps that you have been using probably can achieve good recoveries for these new molecules. Here's a case study where groundwater from 4 AFFF sites in Canada were prepared by direct aliquoting because of their high levels. The 4 sites have different firefighter training histories. The figures shows the sum concentration of 5 superclasses, carboxylates, sulfonates, fluorotelomere precursors, and ECF precursor, and other PFAS that don't fit the description of the other 4 classes. So site 1 still has active firefighter training activities, and not surprisingly, we observe very high level PFAS in groundwater. know the predominance of fluoropolymer and ECF precursors. Site 2 and 3 have similar AAA use history in terms of duration, but site 3 and 2 actually have a different profiles. But site 4 was closed down about 15 years ago. Actually, soil was remediated for petroleum hydrocarbons. So coincidentally, PFAS level were quite low. We think just because of kind of overlapping of the contamination. Still, for this closed site, precursor were detectable at similar levels as polyfluoroalkyl sulfonates. What I'm now showing here is that most of the precursors we detected in groundwater actually are not zwitterionic or cationic PFAS, but anionic compounds such as 6,2-fluorotantamide sulfonate or other type of anionic transformation products. So this means current analyte list published by UIC EPA probably can cover most of them. Still, for selected locations, we discovered that zwitterions can still make up a large percentage of a total PFAS mass, up to 50%, but only in selected locations. In our lab, for less contaminated water, such as drinking water, we mainly use automated large volume solid phase extraction apparatus. So this kind of setup allows concentration as high as 1,000 times, and it can achieve accident detection limits. So here I just listed some number here. So electrospray ionization positive, negative, ESI negative means anionic PFAS, and ESI plus means mostly zwitterionic and cationic PFAS. You can see the levels are much lower than the 70 ppg level for US EPA drinking water limits. The automatic system we have in the lab only have 6 positions. Although they can save a lot of manpower, but we still find sometimes when you have a large number of samples to process, it's going to take a long time. And also when you come to solid phase extraction, very short chain polyfluoroalkyl acids and very long chain ones tend to have issues such as early breakthrough or sorption artifacts. But these issues are not specific to AFFF sources, but to PFAS from all other sources as well. So here I just want to present another case study. So we conducted a province-wide drinking water survey for Quebec. Over 460 samples were collected from 370 municipalities. So this talk about public drinking water. In terms of the source, 44% were from surface water, 46% from groundwater, and the rest is a mixture of different sources. So as far as we know, Quebec actually doesn't have large or significantly impact AFFF sources, or doesn't have much industry related to AFFF or other kind of PFAS. So significant sources are not known. But still, when you look at the detection frequency in these water samples, not surprisingly, PFAS, PFAS-A, and they're also long chain, short chain analogs kind of appear at high frequencies. So here I'm showing frequencies. And in terms of precursors, the most often detected one actually are FBSA here and FHSSA. So these two are amides, 4 and 6 carbon equivalent of FOSA. So FOSA, remember, I think is covered in one of the US EPA methods. And the other kind of frequently detected precursor is 6,2-fluorotantamide sulfonate, 6,2-FTSA, and its compound also show up very often at AFFF sites. For zwitterionic PFAS, these are the ones labeled by the star. So you can see they have really low detection frequencies, only appear in specific watersheds and locations. And then this data just shows that, at least for the province of Quebec, we don't actually have a serious impact by PFAS for drinking water. So all the concentrations we saw were well below Health Canada or EPA guideline value set for PFAS or PFAS-A. Now let's look at the method for solids. So different from water matrices, we actually found the most popular soil extraction methods actually cannot recover these new molecules well, especially for soils with high organic matter or clay content. And sometimes we see like recovery value as low as a single digits. So if you would consider integrating these new molecules in your project, it's very important to take a closer look at the soil extraction and preparation procedures. Over time, we have gone through several rounds of method update. So method listed here are the ones that would work. So mostly these are the methods just using methanol plus either a concentrated acid or concentrated base or concentrated salts such as ammonia acetate or a combination of them. So just one thing to remember is some PFAS, these sweet ionic molecules do undergo abiotic hydrolysis under extreme pH. So the use of a strong acid or base should be monitored closely. Now we have gone to the method number 4. This is method that we really like. It works for different type of solid matrices and also have, allow sensitive instrument detection. So here is the same case study again, that for A2PFAS site in Canada. So what I'm showing are the PFAS concentration in surface soils. Again, as you can see for site number 1 that still has active firefighter trainings, the profile is predominated by fluoropolymer-based precursor. Well, this has to do with the fact that we are switching to fluoropolymer-based A2PF because after 2013, ECF-based A2PF are not permitted in Canada. Again, site 2 and 3 appear to have similar A2PF uses history, but their profiles are very different. Site 2 somehow still have elevated level of these precursors, and site 3 has elevated level of sulfonates. So we're talking about sites that were closed, more than about 20 years ago, and we still detect, precursors. Again, site number 4 were closed down and remediated, but we still detect precursor at comparable levels as, the sulfonates. Again, the same message. So these new molecules are very important for, A2PF impacted soils. If you have read this recent study by Nicholson that described a DoD site in Florida, you may recall a similar message. So it's not only limited to the sites in Canada, but it seemed to be quite a universal phenomenon. So although we developed the method for soils, we also tested, with other type of solid materials, such as, compost from household, and also several types of farmyard solids, such as, cattle manures and poultry litter. So these materials have really high organic carbon content, quite nasty and quite hard to work with. And our method shows robustness for more than 50 analytes. what I'm showing here are representative, sweeter ions and cations. They all showed, very good recoveries. And we analyzed a bunch of, organic waste materials, and we found significant changes in the profile over time. So in here, I divided PFAS into 7 superclasses. So the positive sign means, sweeter ions and cations, and negative sign largely means anionic PFAS. You can see that in 1997 sample, it's the EI sign negative compounds such as, sulfonates or sulfonamides were the dominant ones. But when you move to 2013, 97% of the summed PFAS were actually fluoropolymer ESI positive compound. These are fluoropolymer sweet ions and cations. So what we saw in this 2013 sample is it's not an isolated sample, but across 26 samples, we detected by average more than half of the PFAS compound in there actually are sweet ionics, but most of them are fluoropolymers. So why is this important to DoD? If we only look at A2PF signatures versus other very specific sources, such as landfills or electroplating facilities, we may arrive at the conclusion that any detection of these sweet ionic PFAS should be linked to A2PF contamination. So this study shows that this compound could be used in other applications and then show up in urban domestic waste or probably even wastewater. To quickly recap, really based on our monitoring data, so AFFF remains a major source to sweat ion and cation PFAS, but other sources cannot be ignored. In terms of PFAS chemistry, so we tend to see kind of transition from the ECF to fluoropolymer based. So these are some representative structures. I want to mention here that there are actually two major types of fluoropolymers. So here we have this called X2. This is a beta-ene. This kind of X2 compounds tend to appear in both earlier and also recent samples, but the X3 polymers were only detected in very recent years. So far, I have not seen many studies reporting X3 fluoropolymer in the US, but we have detected them quite often in Canada. For PFAS methods in plasma or serum, I'm not going to present data, but I just want to mention that with advances made in analytical instruments, detection limits have improved by order of magnitudes, so methods have evolved significantly. So one of the earliest methods reported by Leeson and Hagen in 1980 required 25 ml per analysis, and the detection limits were around 15 nanogram per ml for PFOA in plasma. When it comes to 2001, the Hansen method, that one was based on iron parent extraction. So it required about 0.5 ml and then to reach a detection limit about 1 to 2 nanogram per ml. So over time, the sample intake has become so small, and then we even saw a study by Mao and Wang in 2015 that reported the use of 5 microliter to get to a detection limit of less than 1 nanogram per ml. So now routinely, we actually use about 40 ml for plasma or serum analysis, and we actually don't really need iron parent extraction because the level of PFAS in blood samples appear quite high relative to instrument with a solvent such as acetonitrile. Oh, sorry, I jumped. Okay, acetonitrile can just denature the protein, and then the samples afterwards can be injected into instrument directly. And now we are working on improving methods for fish. Like always, we first reevaluate all the primary literature methods. So 6 out of the 10 methods we tested showed acceptable performance for PFAS in this case. Note, two methods didn't work well. For instance, this particular method uses acetonitrile plus amine carb cleanup, can only reach about 20%. We also found that if samples contain, kind of a high amount of long-chain polyfluoroalkyl acids, and cleanup using this kind of solid phase extraction tend to actually decrease absolute recovery. So this needs to be done very carefully. We just secured, fish sample that were exposed to AFFF. So next step is for us to test, how well the method can work for these new molecules. So now we are less than halfway through the project. So you may notice that we didn't talk about the sediment matrix. So this is going to be the last solid material to test it for the solid method. Of course, a major focus in next year and 2 are going to be the biota samples, so fish tissues, avian plasmas, and then various vegetation samples. We for biota sample, we hope to have a single method that could work for different type of materials. And in the meantime, we're also going to test and compare the efficacy of a matrix effect reduction approach using several different LC-MS platform to ensure our method is robust. Along the way, we actually have added a new task to evaluate sample storage holding time and also possible filtration and sorption artifacts. We are now in the middle of a long-term test for surface water samples. I don't have time to talk about the top methods. So for top methods, total oxidizable precursor analysis, we are working on switching from heat activation to actually UV activation. That way we can greatly shorten the acid time, and also that allow us to include some preemptive treatment to improve the oxidation yields. For total organofluorine analysis, we will compare the conventional combustion ion chromatography method with a new method that use atomic absorption instrument. That instrument has more options for sample pyrolysis and have a more definite detection of a fluorine signature. To summarize, so for existing water sample procedure, they largely applicable to this new new sweet ionic molecule. But for solids, the stories are very different. New and improved extraction methods are necessary. When it comes to biota analysis, now we find that sample size, smaller sample size can work and still allow sufficient detection and also present actually less matrix effect. When it comes to these standards, although we have some standards, but we still need isotope label standards, and then this can allow us to further improve the analytical precisions. And lastly, just want to mention that sweet ionic PFAS also relevant for some non-HWF sources, and which bears some implications for the people who interested in PFAS environmental forensics. So we hope eventually publish detailed methods and procedures. So we will include not only the final method, but also document the process, what works and how we get there, and also talk about the failures we actually experience, so that can, I think that's going to be very helpful for other people want to adapt slightly different methods, but if they don't want to exactly follow our procedures. We're also going to publish and document key monitoring findings to illustrate the applications of these methods. Last, I want to acknowledge my collaborator students, Sebastian, Gabriel, Sang and Min, for their hard work, and also staff members at Transport Canada and Dr. Melanie de Houzy for providing different type of samples. I especially want to thank Dr. Gabriel Munoz, who is critical in the entire project, who has always surprised us with his amazing skills and new discoveries. So that concludes my presentation, and thanks everyone for your interest and attention.
Thank you so much, Jen. We did receive a lot of questions. We'll start off with some of the more basic ones. Can you tell us how stable zwitterionic PFAS are during storage in preparation for sampling?
Okay, so I don't have definite answers to cover all the possible, compounds, but we have completed a drinking water stability test where we actually dechlorinated, drinking water, and we tested various components at different levels in drinking water. And after 1 month, these molecules appear quite stable. But right now we're doing the surface water test. That's going to involve some sort of, microbial activities. That's where we have some concern. But right now we don't have, definite data to report. But in terms of sample preparation procedure, I think I mentioned when you use a very high pH or, very strong or possible hydrolysis of certain compounds.
Great, thank you so much. This next question is from the Navy Marine Corps Public Health Center. What impact do fluorine-containing pharmaceuticals have, if any, on PFAS measurements in surface water?
That's a great question. We haven't gone to that part, but I believe first is really sample specific, right? If we talk about sample from HWF sites, I really don't expect, other type of fluoridated compound have a strong impact. Maybe the story is going to be different when we talk about wastewater. But if you think about PFAS, right, each molecule carries so many fluorines, and usually, if they are present at a significant level, that fluorine signature is going to be very obvious. So yeah, right now I just don't have really a definite answer yet.
Great, thank you. Here's a question from Clemson University. How should the two different solvents you described in methods 3 and 4 be used to extract PFAS from solid matrices?
Okay, so if we want to go, this is regarding the analytical details. I don't know if it's possible to go to the slides. Do you have the slides number?
The slide number was not provided. So we can just go back to maybe one of the two slides, maybe method 3, Laura.
Okay, so your question is how we're going to use, how different these two methods are, right? That's what I understand is the question. So method 3, what we found, let me just bring out my slide on my screen. I just want to look at the detail because I don't remember exactly the
slide 39, please.
Yeah, I'm gonna go there. Oh, okay. So how different? Okay, now I understand. Okay, so usually we actually prefer a method that avoids strong acid. So if the method is intended for LCMS analysis, we like to use method number 4 or method number 2 even. But when the samples are going to be also used for top analysis, top assay, you definitely want to avoid ammonium acetate because that's going to interfere with the top assay. So again, if sample want to prepare for top assay, go for number 3 because it doesn't have any carbon material in the solvent. I hope that answers the question. Pretty technical question.
Thank you. Yeah, thank you so much, Jen. Okay, we're going to take maybe 1 or 2 more questions before we turn it over to Jennifer. Are the new methods for ZPFAS in soil and water commercially available, or are they specific to your lab? And if they're specific to your lab, are you planning to, do you know of any efforts to commercially develop these methodologies?
As far as I know, they are not commercially available yet. Really, we are not going to commercialize any of these methods. They will be published either in the form of guidance documents on CERDP website or published as peer-reviewed articles. And people can go into these articles or go into guideline document, find the detailed procedure. We usually provide very detailed procedures in our publications. And I hope eventually, some commercial lab would pick up some, some compounds, such as the short-chain amides, and I found they are important for drinking water.
Great, thank you. And one final question related again to zwitterionic PFAS. How did you get the chemical standards for these compounds?
So early time, we did have some customer synthesized, but over time, so Wellington Lab has made most of them that we use. We have 2 more that we only have in our labs. These are called amine oxides, but later on we found they actually, amine oxides a lot of times are not really important compounds. If any compound turned to be kind of abandoned in the environment, I'm sure one day some of these commercial labs like Wellington will commercialize the material because there's a market need for it.
Great, thank you so much, Jen. Again, we have about 10 more questions that have come in. We'll try to get to them at the final Q&A, but I'd like to go ahead and introduce our final speaker, Dr. Jennifer Fields, who is a professor in the Department of Environmental and Molecular Toxicology at Oregon State University. Jennifer's current research focuses on the development and application of quantitative analytical methods for organic micropollutants and their transformation products in natural and engineered systems with a focus on PFAS. Jennifer was a pioneer in the area of PFAS occurrence and behavior with a focus on groundwater contaminated by firefighting foams, municipal wastewater treatment systems, and in municipal landfill leachates. She served as an executive editor for Environmental Science and Technology and was an editor for water research between 2004 and 2008. And finally, Jennifer earned her doctoral degree in geochemistry from the Colorado School of Mines. Jennifer, please proceed.
Good morning, good afternoon. It's a pleasure to be part of this webinar today. And what you're going to see today is a compilation of our best hits when on a project where we're set out to look at potential for bias, specifically with respect to field sampling. And we'll just move on. So the presentation outline is like, why are we looking at this question? And followed by what our exact SERDP project objectives are. I'll give you an idea of some of the representative results, moving on to conclusions, and finally, benefits to this DoD. So why would we look at the potential for bias? Well, if you've watched the literature for quite some time, this is not a new idea. There has been lots of suggestions and indications, particularly in the analytical literature, that there's this potential for stratification. And more recently, people really interested in air-water interface. So how can bias occur? Well, stratification is one possibility. And what this means is if we have processes that can cause potential artifacts or distorting, say, the distribution of PFAS in environmental matrices, particularly water, what we may get is a different answer than what we would expect or what the actual, say, bulk answer is. So we're very curious about the possibility of artifacts. One is due to the backgrounds of PFAS. We're quite well aware now that PFAS can be found in some common laboratory materials and some field sampling materials. And if those materials give their PFASs off during the time of sampling or analysis, could result in positive bias of the measured values. When we think of processes like stratification in a water column or filtration, that's actually well known. Absorption to containers is another issue that's been raised in the literature. And these processes during sample storage and analysis, this possibility can potentially result in a negative bias. And so when we look at negative and positive bias, what we see is this PFAS surface activity is pretty important. And so PFAS accumulation at air-water interfaces or other interfaces is really an important process. What causes that? Well, Caio Vegas did an interesting piece, and his paper was titled, "What Makes PFAS So Special?" And it's essentially those carbon-fluorine bonds have very weak van der Waals forces between them. And that means those electrons are really not sort of wobbling around. They're very firmly held. And what you get is a very low tendency to interact with itself or anything else. And so this inability of PFAS fluorinated tails to interact, say, with water in a positive, attractive force means that's essentially water's driving it out of solution to interfaces. And that's why interfaces become quite interesting. We actually rely on interfaces, say, analytically, like when Jen was talking about SPE. We're relying on that partitioning to that interface, solid water interface, for analysis. So partitioning interfaces, if we can control it, we can use it for analytical purposes. If it's not controlled, then we can say, well, maybe there's bias that can happen inadvertently when we're sampling surface water, groundwater, and that's why we're taking a close look at storage and sample bottles, and even analysis in autosampler vials. So you get an idea that there's many ways in which bias can potentially enter all the way from sampling to analysis. This project actually looks more at field sampling. And Jen, for example, is taking a really hard look at the actual methodology. So this project's objectives was actually to take a look at the field materials that are actually used during field samplings, as well as some procedures, and to examine it closely to see if bias potentially exists. And of course, the idea is if you can identify it, then you would potentially eliminate bias. And it's really focused on field sample collection. The second one was to impact the sample hold times to eliminate bias in PFAS concentrations. The good news, this objective was set up early prior to a great publication by the Axis Lab and Wooden et al. They actually came up with a great paper that really talks about sample hold times. And so I would refer people to that. And since that was such high quality, we didn't need to do this particular objective ourselves. So I refer you to that published paper in Environmental Science and Technology. The third objective was to take a look at PFAS stratification, the potential for it in water columns. And we're thinking monitoring wells as well as surface waters. And if we see significant stratification, to identify sampling approaches that would minimize the potential for bias. So to the field material testing part of the project, we obtained either by purchase or donation 66 various materials actually used in field sampling campaigns. And this was done, my great collaborators who are all listed at the end of the presentation, we'll get to that here in a bit. But these 66 materials broke along 4 categories. Materials that you actually use prior to the arrival at the field site, we call that pre-staging. So they're not actually used in the field. Staging, where you're actually in the field preparing to sample, the sampling process itself, the active, say pumping out water, putting it in a bottle, and then post-sampling, what's used after the actual sampling is over, think shipping. And so we had those 66 materials, they fall in those categories. We took an aggressive approach to kind of look at worst case scenario. So we extracted with methanol, pretty straightforward. So it's not a leaching study. Those are out there for your, you can see those. But we took this approach to, again, create a worst case scenario. Since we think methanol extraction is much more likely to give you, higher values than, say, aqueous exposure. So just a snippet of results here. So actually, if you look on the right-hand side, you look at photos, you might recognize various types of blue ice. You might recognize Teflon tape, which is the second one down, and you might recognize aluminum foil. These are all materials that are on one or more guidance documents as being prohibited. And what we found, we looked at 6 brands of ice packs, and we could not find any of the PFASs above our method detection limit. And that's inside and outside. So if like you had a leaky ice pack. So we didn't see any positive hits for the blue ice. Yes, you can see trace levels of PFAS on PTFE tape, which is again that tape in that bottle here on the right. And you can see we got a combination of PFOS or PFOA, but then you ask yourself, well, let's see, based on that amount that I was able to extract, how much PTFE tape would I have to have inside a 1 liter bottle, completely desorb, and what level of PFAS would you hit? So you'd actually have to have 130 centimeters of PTFE tape in that 1 liter bottle and release all its contents to get or to reach 70 nanogram per liter. And so you would look at that image and go, yeah, that's probably not realistic. Same likewise in the upper right. 6, if you, at the ice pack brands, if you assume 1/2 the method of detection limit to give yourself a number, you need 6 of those in that inside that 1 liter bottle to completely desorb this less than LOD theoretical limit to get you to that EPA HAL. So you can see that kind of, extreme scenario is quite unlikely. Likewise, aluminum foil, different aluminum foils that gets used in the field, you cover things with it, you can find non-stick aluminum foil, that's what we analyzed here. Yes, you can measure residues on there, but based on the residues and this gross assumption that all of those residues would leach in water, you would have to put 26 centimeters squared of aluminum foil in that bottle to reach that EPA HAL. Now, I realize EPA HAL is just an example because the method detection limits are dropping, but it's really done for illustrative purposes that we have these concerns about the materials, but then you have to really think about pathways. Is there a way for those residues plausibly to get inside that bottle to potentially impact that, in this case, water sample? And the answer is, in these cases, those pathways are very implausible. The other thing my excellent team members did was to actually go and review their own data sets. My consulting friends have access to very large databases. And what they did is they not only reviewed the literature, they looked at these databases and said, if we look at our positive equipment field blanks, do we see consistent positive hits? And if so, for what materials and what practices? And so on the cartoon on the right, you see that they together looked at a database that crossed 57 US DoD bases. They did find 279 positive equipment blanks. And of those, 64 gave values above the LOD. 38 of those, 38 gave greater than 1 nanogram per liter, but only 4 came from 2019 to 2020. And so what they concluded was there does not appear to be any equipment or practice that is currently happening in the field that is systemically or systematically creating positive bias in the measured PFAS values. At the end of that exercise, we did end up with one pressure transducer that was identified out of one of those 4. We brought it into the lab, it was donated, we extracted in methanol and found nothing above the limit of detection. And so from that exercise, we basically concluded there's no systemic bias with regard to field sampling procedures. And that's why equipment blanks are so useful. They really give us that insight. So in this field materials section, we basically concluded most materials don't come in contact with the sample. And so when you're looking at your own practices in the field, you can ask yourself, if I have a concern, but is there a pathway by which that material could actually impact or contact that in this case, say, water sample. So it still seemed prudent to avoid fluorinated materials. PTFE is an obvious one, even though the risk might actually be low. Seems to be a reasonable thing to do. The other conclusion was the team decided that current sampling practices, which people have taken a very close look at, are really well established and do seem to be preventing cross-contamination and really minimizing the potential for positive bias. If you're interested in the field sampling materials paper, it is open access. It is by Radoa et al., and it is available on the American Chemical Society website under ESTCP letters. Moving on, stratification in groundwater. Because of recent interest in air-water interface, there was an interest in trying to understand, well, could this possibly impact the measured concentrations in a groundwater well. So we actually set up model groundwater wells, just a short section. This is about as taller than I am, which isn't very tall, about 6 feet, and filled with actual groundwater from Woodsmith Air Force Base. And it had a variety of carboxylate sulfonates, telomere sulfonates in there. So they're made of typical construction material out of, so it's representative of wells. So we had the low ionic strength well water from Woodsmith, and then we also just increased the same water, the ionic strength of the water, to look at low and high ionic strength, because of course we have sites that are brackish or impacted by saline systems. And then we had a control well. And these ports are sampled at times 0 and 3, 3 ports, times 0 at 0, 3 months, and now 6 months, to simulate inactivity, these quiet periods of time where wells can set between sampling events, to see if the differences in the water column are measurable. And the key finding was that we don't see significant differences in PFAS concentrations measured at the high and the low and the intermediate ports. None was actually at the interface, because no ports are actually at the interface. We typically don't sample that, especially during low flow. So what low flow sampling. So we decided, from this data, we decided that groundwater sampling methods at present don't really need to be modified, because while stratification can certainly be occurring, the impact on the total mass and the distribution in the water column is not evident in the analytical measurements. So just as a cartoon here, yes, you can have some PFAS accumulating at the air-water interface, but given the typical diameter of a well and the total water column, basically you can actually calculate what you would expect up there, because there's some great work by Kurt Pinnell and Mark Brousseau and Charles Schaefer, who have actually looked at this in accumulation at the air-water interface. And so in a low ionic strength system, about 0.3 of the mass of PFAS would actually be at that interface. And 0.3, migration of 0.3 of the mass to the interface does not cause a significant change in the measured aqueous concentrations at any depth in that well. Higher salinity, you would predict about 2% of the mass would be there. Again, not something you can really measure, because analytical methods have variability about them. So the punchline is, especially given low flow sampling type designs now, when people sample, it's really designed not to disturb the entire or include the entire water in the well column. And basically we conclude that this phenomena is not of concern with regard to potential bias in field sample data. Another type of field stratification that can occur is accumulation on surface water. So here you can see very large surface area. And so Doran Bogdan of AECOM in Michigan had been talking quite a bit about that. There's a lot of activity in Mission, so we got the opportunity to take a look at some of the foam and some of the lakes up in that particular area. And so you can actually see it here on the shoreline. You can also see the kids in the area. And so the question is what is the PFAS accumulation in there? And there's some great work out there in the states, by the way. Minnesota and Michigan, and I think also Wisconsin, are very active in this area. So we got the opportunity to contribute to that knowledge. And then if you measure the bulk water and the foam, you can provide what's called an enrichment factor. And there is some information on enrichment factors in the literature, especially for aerosolization and natural seawater, but not for freshwater, and especially not for near PFAS point sources. So we took 8 pairs of foam and bulk water from a freshwater lake. It turns out foam is very viscous, and when you let it settle, it's high in organic matter. It's got a lot of particulate matter. It's this nasty sample in the lower right. And if you try to extract it, it's very gelatinous. And so we just did a simple 1:5 dilution into methanol and analyzed for not only DOC was analyzed in the water sample itself, but then in the methanol dilution, we looked for 50 target and quite a few suspect PFAS. So what did we see? Foam indeed can carry very high concentrations. The highest we saw was 97,000 nanogram per liter. That happened to be PFAS. Right off the end of this, what you see here is a map of the lake. These colored zones, of course, are PFAS zones, and you can see the interface between where those groundwaters discharge to that surface water. Not all foams were that concentrated, but that's certainly the highest one we saw, and that's radically different from the bulk water immediately below it, which only reached up to about 50 nanogram per liter. So there is a strong enrichment into foam. Foam contained long chain. The carboxylates were primarily linear, which are probably degradation products of telomere precursors and AFFF. And you can also see the branched and linear sulfonates in the foam. We also saw what we think of as sort of indicator PFAS in the foam. So AFFF, those linear carboxylates are kind of a clue of transformation of precursors from telomeres. We saw peaches. Peaches is not just like a hydraulic fluid thing. It is also in AFFFs. And then the C6 amide, the FHXSA that Jen mentioned, is very much in surface waters, and I concur with her that that compound is very mobile and very soluble, and there was a great piece of work by Scott Mayberry's group that showed how ubiquitous that compound was up in Canadian waters quite a few years ago, and that appears as well. And then landfill leachate, our indicator compound, the 5-3 FTCA, was in foam number 6 here in the upper part of the lake. That is indeed, there's a former township dump just upstream of that, and that foam seemed to capture that indicator compound. Oh, if you are interested, this foam work was published in Environmental Science and Technology last year by Trevor Schwichtenberg. Moving on, enrichment factors. So that's just a simple concentration of foam over the concentration in water, and we see that the enrichment factor can range up to 4,400 in the case of PFAS. And the branched and linear have their own enrichment factors because they are different molecules. You actually see that the linear molecules are enriched more than the branch because they have a larger hydrophobic surface area. In terms of, so you can actually see this rough relationship with retention time on chromatographic retention time. It's a good proxy for hydrophobicity, and indeed for real field samples, which, field data is kind of messy, you actually see that the enrichment factor, the log of the enriched factor, is going up with retention time. You would expect that, but you do see quite a bit of variation in the actual enrichment factors. Now, where is this coming from? We definitely looked at the DOC. DOC is very high in all the 8 samples, very high, very uniform, 250 milligram per liter. So we're orders of magnitude higher DOC than the PFASs. DOC also enriches in the foam, about a factor of 18, not as strongly. Actually, that's what the horizontal line is here in the graph. That's actually the DOC enrichment factor. So you see PFASs are more surface active than DOC as they get to be longer chain lengths. It appears that the foam is likely of a DOC origin because the DOC levels are so high. And the PFAS concentrations, even though they are quite high for surface water, they are nowhere near the critical micelle concentration, which is typically where solutions begin to foam. So foam is really a complex solution. It is likely driven by dissolved organic carbon, and PFAS may be contributing and or certainly hitching a ride on that foam. Turns out foam is not easy to make in the lab, and that's actually part of an ongoing part of this project. In terms of, what does this mean for surface water collection? Well, we thought about, how is surface water done? How's the collection done now? Probably done in a variety of different ways. You might side fill a bottle, particularly if you're in a shallow pipe or say a shallow water body. That's where you might actually introduce a significant quantity of the surface microlayer and or foam, depending on what's present. Or you might go down through a surface like in the cartoon at the bottom and actually hit a smaller cross-sectional area. So we played around with our numbers, what we're seeing in surface microlayer, which I didn't discuss. What do we see in foam? And we took a quick estimate of how much of that microlayer you might capture, and it turns out, depending on what the concentration is in the foam or microlayer, you could bias your water samples. And here's an example. If you assume that the bulk water below the foam or microlayer is at or below your limit of quant, which or let's say a low number like 2 or 10, basically capturing how much microlayer you capture can really increase your apparent concentration. In the case of the scooping, you capture about 0.6 mils of a surface microlayer based on that surface area and the depth of microlayer. And you could get values that vary from 1 nanogram per liter, which, as you just heard, is now within range, up to 58 nanograms per liter. So we want to bring folks' attention to how you sample could have some bearing on the measured values in the case of surface waters, because bulk water typically, especially if you look at long chains, is really low. But that's not true in the microlayer and or the foam. Okay, trying to get here to the end. So sampling guidance. So this is kind of harkening back to the field materials. The team extensively peer-reviewed publications, as well as taking information generated from this project. And they created a synthesis document. And so the whole goal was to synthesize published as well as information from the gray literature and from this, this project, and to really synthesize it and look, you know, at groundwater, surface water, our field sampling materials, et cetera, soil storage stability, and put it in a document for everybody's reading pleasure. The team also surveyed practitioners from the ITRC team. A shout out to those of you who participated. Thank you very much. Again, collecting and synthesizing data from as broad a group of stakeholders as possible, and all that information has now been curated in a sampling guidance document. There will be a link here in just a moment, but the report was submitted back in January. The Certu team has then given their stamp of approval, and now it is available on the Certu website. And what you'll find in there is that synthesis of the field equipment materials, the current guidance document protocols or recommendations, again, synthesis of information, great information from the literature on sample storage, and our current stratification results. There are some recommendations. What we find is that some of the guidance documents are overly protective, which isn't a bad thing, but it might come at a cost. So if you take a look at that, there might be a chance to revisit some current protocols. So overall, conclusions here is that our current, the goal was to improve our current guidance with data, and to consider whether the field conditions and our current practices are actually impacting the results, and then to really encourage people to think about whether a plausible pathway exists when you're thinking about field materials. One of the conclusions from the Woodness study is very high stability of PFAS in frozen samples. I don't think that's industry practice, but it's good information to have in the literature. Collecting surface waters, at the moment, it appears prudent to avoid any obvious foam and potentially avoid the surface microlayer, especially if you are in a AFFF discharge zone. And it doesn't appear that changes need to be made to sampling methodology for groundwater. The stratification, if it's occurring, is likely to be trivial with regard to the potential for impacting bias, and this guidance sampling document is now available. So in terms of benefits to the DoD, we took a science-based approach to put data out there and really shine a light on which materials, if any, can potentially cause bias. Again, bottom line is many materials really are not in a direct contact, thus there is no plausible pathway. So we can rethink some of the things like blue ice. It's very green, it's recyclable, and it's really not, it doesn't seem to pose a risk, because we all would want to reduce waste and avoid unnecessary field time and expenses. These extended hold times, if we now know that it's available, freezing does provide very, very long-term stability, especially for matrices that are microbially active, like the Woodness study pointed out, that if you are in microbially active matrices, like wastewater, there are compounds that can be biodegraded to the sulfonamide can biodegrade to acetic acids. So you want to keep that in mind and really, take a good look at that piece of literature. And then our goal here is to provide improved surface water and foam sampling guidance, as well as sampling methods. And so to conclude, here's these fantastic team members: Trevor Schwitzenberg, PhD student here at Oregon State, Doran Bogdan of AECOM, Rula and Elizabeth of Geosyntech, Bill and Amanda from CH2M, Jacobs and Charles Dina and Dung from CDM Smith. And as promised, this link will take you to our project website, 1205, and on the right-hand side, you will see a technical report, and that is our current sampling guidance document. And thank you.
Thank you, Jennifer, for a great presentation. We got a lot of questions. The first one is from the EPA Office of Resource Conservation and Recovery, and it reads as follows. If PFAS enrich in foams, could a foam-forming surfactant be used to manage PFAS impacts and contamination in surface water?
That's a super question. There are already there was something called the hydrocyclone technology that was, I think, invented by the Air Force quite some years ago, and it creates a foam, and some variations of that approach are now in practice in Australia. There's a group in Florida who is using foaming as a way to enrich and pull off. I think Ian Cousins in Stockholm has also done that. So foam as a engineering tool has been around for a long time, and I do think you can see now people who are utilizing that as a way to remove PFAS from water bodies. Whether it can be done on the scale of a surface water, that's an excellent question, and I will leave that to our friendly engineers to answer that question.
Thank you so much, Jennifer. Despite your findings and the guidance document that your team developed, if our audience members are living in a state and practicing in a state where PFAS state sampling guidance is available, would you advise that they take shortcuts based on your guidance or follow the state sampling protocols?
Well, I would always follow your state sampling protocol. We put out these guidance documents, the recommendations to, I think it gives more flexibility, but I think each state will have to take their own view of that information. And so we have at least provided the information so that people can make more science-based informed decisions. So no, we would not say to override your state recommendations, but perhaps the guidance document can inform future versions of guidance documents adopted by states.
This is an excellent point. Thank you, Jennifer. The next question is from the Minnesota Pollution Control Agency. And the person that asked the question states that their understanding is that surface water foam is ephemeral. It may form with turbulent conditions and dissolve during calm conditions. So the question is, does avoiding foam or the surface microlayer underestimate total PFAS concentrations in a water body?
Well, super points, and a shout out to Minnesota, who's done some really very good work on foam themselves. And I would agree, foam is a very ephemeral phenomena. It's transient and it's dependent. You know, what's interesting for us is we now have measurements of the surface microlayer itself using a glass plate. We compare it to foam. They're very different. And so we don't yet understand the connection between surface microlayer and how it becomes foam, or foam goes back to the surface microlayer. So that's really an interesting process right now. In terms of understanding if it's underestimating, I guess it probably depends on what your question is. If you are thinking about bulk water, and for organisms that maybe make their living in bulk water, taking a sample below the surface might be prudent. If you are thinking about recreational swimming and perhaps human exposure or emergent insects that live at that air-water interface, capturing that might be very prudent. So I think the goal here is to highlight where PFASs are hanging out, to help people think through their own goals for sampling and for thinking about exposure pathways, and giving people the flexibility and the data to make informed decisions about what they want to do in their own sampling campaigns.
Great, thank you so much, Jennifer. At this point, I'd like to pull in Jen and Janice and ask you guys some broader questions that have been coming in. And if we have time, I'll get back to you, Jennifer. So my question, and maybe Janice can start by responding to it, is in which direction do you think analytical methods should go and why? So Janice?
Oh, that's really broad. Meaning, I don't know if they need. Oh, yeah. No, I think that, you know, there's a lot of method development currently being done by the EPA on some methods that are could prove very useful for the DoD in the future, for like total organic fluorine methods for, you know, drinking water and other environmental media. Definitely, I feel like we need to have a method that is capable of giving a sum of PFAS in general. Besides that, I would say that, looking towards some of the methods that that Jen is working on relative to some of the other analytes, and also, we're still looking at OTM 45s coming out for error analysis, and looking at a defined method for targeted analysis and non-targeted analysis. Analytical methods for error analysis, I think, would be beneficial, because we really don't have a lot. Nobody's really done a lot of work on the volatile side of PFAS, and I think that that's where, we're going to see a lot of movement in the future.
Thank you so much, Janice. This was a perfect response. Jen, do you have something you'd like to add?
What I'm thinking is maybe the folks from commercial lab will not agree with you, but our experience is just because the type of PFAS molecules, there's so many of them, we actually really rely on high resolution, LCMS instruments, and their cost has been coming down. And I just find if the methods have, use a high resolution instrument, that really allow you to see, a bigger variety of, compounds, and also allow you to do semi-quant analysis. So this is something I think could be a trend, but, like I said, it can add to the cost of commercial analysis, and people might not agree with my approach.
Thank you, Jen. Jennifer, anything you'd like to add?
Oh, yes, I think as people try to make decisions, and I'm seeing a strong trend toward forensics, who done it, whose is it, whose PFAS is it, and methods that help assist in differentiating sources or proportioning sources are very, very much needed. And so with that in mind, I want to make a shout out to our SERDP project with the Colorado School of Mines and Cornell and University of North Dakota, and that is ER 1375. And our first goal in this forensics project is to unify our analytical. So we are taking a very unified approach to look at wastewater effluent, biosolids leachate, groundwater source zones, landfill leachates, and industrial effluents, unify the analytical, and then put it through a target and suspect, and non-target is, well, non-targeted acquisition, but then target suspect output, and then through statistical tools identify which of the PFAS are actually a marker for those unique sources. And then from that master multimedia analysis, come up with what we termed in our original proposal, the forensics panel, the panel that will help you decide your sources and your impact in, say, a surface water where mixing or a groundwater where two sources can be mixing together, or the source is ambiguous. And so that is our goal and our contribution that will be coming up through the SERDP 1375 forensics project. So it's really for decision making.
Thank you, Jennifer. And while I have you on the line, we're going to go ahead and wrap up. I have one last question that just came through from the Wisconsin Department of Natural Resources. So it's for you, if you could please answer it. Below the surface microlayer, would you expect any variability in PFAS concentrations in the water column of stratified lakes as you sample down to the sediment water interface? If you could answer it in a minute or less, I would be grateful.
The big differential is the surface microlayer and foam, whereas the bulk water seems to be rather uniform. And when we do multiple samples, the precision is quite good.
Great. Thank you so much, Jennifer. And thank you so much to our three speakers for a very engaging webinar. We're going to go ahead and wrap up. I'd like to remind you that our next webinar is in 2 weeks on Thursday, June 17. It will be in the Resource Conservation and Resiliency Program area, and it will focus on DoD-funded research effort to predict how changing climate conditions impact host pathogen interactions and vector-borne disease transmission. This webinar will feature two speakers, Dr. Corinne Richards-Sawaki from the University of Pittsburgh and Dr. Brian Allen from the University of Illinois, Urbana-Champaign. Registration is open, so please visit the SERDP and ESTCP webinar webpage to register for this and other future webinars through the end of the year. Before we conclude, I'd like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it if you can please take a moment to complete a very short survey that will pop up on your screen. This concludes today's webcast. Thank you so much for your participation.